Yeah, I will wait 1 or 2, 3 minutes more. Then we will start. Let's see if anyone else joins. Okay. My internet connection might be a little bit dodgy today. Outside there is heavy storm going on. I was not sure that I will be able to take today, so just bear with me a little. So we'll start at 6:02 or 6:03 around, most probably. So 1 or 2 minutes more. Yeah. Which chapter are you talking about? Can you please just refer to, like, which week? This week's week 8.
Hi. So not only this week, I was just comparing. Like I was going through the lectures from initial.
Yeah, yeah, yeah.
So I am seeing some topics which was taken in the class. I'm not able to find those topics in the textbook.
So so
So
uh, so
yeah, and in between I hear the professor keep saying the TA in those class to share some papers. I'm referring
yeah,
from the
yeah,
paper like that.
yeah,
Also he keep mentioning. So
yeah.
that's
So one thing I will say that what that professor is teaching is from first edition book. So if you have the first edition book, it is available on the internet. Let me share it with you. Okay.
okay. Oh, okay. Then I am referring to the second edition
Yeah,
maybe.
I
So
also
maybe.
read from the second edition book, but for following the search lecture, I sometimes have to go through the first edition book. Uh, so
Okay.
so
Okay.
if you
So
remember,
you're mentioning whatever I had missed in the classes, it will be there in the first edition.
first edition book. So let me just send
Yeah,
it
yeah.
to you.
The topic which I missed was Cauchy sequence, Green's equation,
Oh,
LP convergence, which I couldn't find in
those
the yeah.
things are also not there. Okay, Cauchy sequence, and
Okay, okay.
I shared one article during the Cauchy sequence class. I if I have the link, I will share with you again. I shared some
Ah,
portion. Okay, let me check if I have it with me now. Give me 1 minute.
no, could you post it in your that Excel format where so that because the chat gets deleted, then it'll be lost.
Yeah,
You
yeah,
are
yeah.
having an Excel where you're showing the
Yeah,
chat
yeah. There also I
in
can
the
add it.
group.
Okay,
Okay,
okay.
okay.
Just let me check once if it is
Yes,
there
please.
then.
Yeah. Okay.
Just give me a second. Yeah, so have a look at this. Yeah. So I have a look at the link I have sent. There is another book. So I found that those Cauchy sequence and all was present here. This Bellman optimality and all.
Oh, okay.
Okay.
I'll go through. Okay.
Yeah.
Thank
So
you.
so in this link, the whole book is there. So I have given you only one chapter, chapter three. But there, chapter 3 and chapter 4 is also there, most probably. In chapter 2 and chapter 3, those kind of things are there. But what I have generally found is that sir teaches mostly from first edition book. So the first edition book, how it is there, I don't know these mathematical terms are there in the first edition book. I haven't checked. But the other parts are there, like this Monte Carlo and all dynamic programming. It was completely from there. And the second edition book also you can follow, but it is just a rearranged version. Some portions are before, some portions are after now. Okay.
Okay.
Okay,
Thank you.
so let me go through today's week 8. So okay, so let's start one week. So hello everyone, my name is Sujay Mukherjee and I'm be taking this live session for NPTEL course on reinforcement learning. This week we will be covering the week 8 course. We will be doing a recap of what was taught, as well as solve some problems related to it. This session is being recorded, and you can ask any question whenever you want to. Okay, so let's begin. Okay. So this week, first thing which we covered this week was so the topic one that was covered was DQN, Deep Q Learning, or DQN, that is probably called. So do you have the PDF version of this book? No, I couldn't find the PDF version of this book. Both the books, like this first edition, also I don't have. I mean, I only found the HTML version there. So HTML version you can read, and this one has PDF. Like this GitHub account has the book entire. This mathematical foundation order. Okay, so let's first start with DQN. So last week we have gone through the functional approximation and those stuff, and we came across defeated Q and all, and least square TD and all LSTD. Now, so you remember what were you trying to solve basically using functional representation? So the problem was with tabular version. So problem with tabular version is it requires time and memory when number of states are large, right? So what is the problem with a tabular approach of Q learning and all was that as we increase the number of states, so what we are previously dealing with were a very small number of states in the chapters. Now if suppose you have number of states of the power of 10 to the power 5, 10 to the power of 10, so storing those, okay, you can today memories are cheap, you can store them, but the problem lies that you have to do the computation, so many computation of value functions and all for each state and each action pair. So one easy approach was that function approximation. So you are trying to do a approximation of the function. So for this topic DQN, what we have is that the story goes around like this. So this DQN is one such algorithm. Okay, so what we have here is that you have an environment. You have an environment and you have an agent. So the agent interacts with the environment. So the agent interacts with the environment, but the reason for its interaction is something else. So it interacts to get a subset of data set. So through this interaction, what it wants to gather is a state, action, reward, and next state. So this kind of pair it wants to generate, like its user trajectory, and try to generate a setup of data set like this. Okay. Next, what it does is it trains two neural networks. Basically, okay, so training two neural network is a very big term, but let's assume for the minute that it trains two neural networks. So the one neural network's task is, so suppose you have given a state and an action. It wants to find the Q value of it. It wants to predict the Q value of it. The other neural network, its job is, so you have been given this tuple you have. So it takes as input next state as input, and it gives the predicts the Q value for action which gives the maximum Q value. Okay, so it tries to find the Q max, right? That action value pair which gives the max Q. Okay, so it is trying to predict the Q max. So these are the two neural networks we have. So this is what DQN main structure is. So if I try to draw it, let me try to draw it. Just give me a minute. So the three components of DQN are, one is experience relay, one is, number two is Q neural network, and number three is target neural network. So this experience relay part's job is to get a data set of ST, AT, RT, and ST plus 1. So it interacts with the environment and gets this tuple. Okay. And as I said, the QN network uses this thing, uses one of this tuple, and its work is to predict the Q value for state action pair. And then you have the target neural network. Its job is to predict max Q value for ST plus 1. Okay, so this is how it does. Now, what does this experience relay's main task is? The experience relay basically does a follow a epsilon greedy approach. Why it is called why it is an epsilon greedy approach? Because This allows you to sample based on some policy, right? It samples like this exploration part. It's happening samples based on some policy. And as you change the policy, because after this after you have trained a QNL and target neural network, you relay those results, like what is the compute the loss. So you compute the loss, okay, loss function after generating the result, and you relay it back to the experience relay part, and that's how it updates the greedy policy, epsilon greedy policy. Okay, so any confusion regarding this, you can ask any question. Yes, which one is predominantly used? Yeah, both. Like you are asking which neural network is predominantly used, or both. So these both neural networks are. Oh, like which neural network is used, or is GPUN is more used? Yeah, no, this entire system is the DQN. This experience relay neural network and target neural network. Okay, so experience relay. Just give me a second. I will show you a diagram. Okay, I will show you a diagram which will be better helpful to understand what I'm trying to say.
Sir, you got my question, right, sir?
Yeah, yeah, I got it.
Yeah. So DQN, we have the say experience relay G network. So which one is used on which set?
Yeah, I'm giving you an example. Yeah, are you able to see this? Yes. Are you able to see this, right? Yes. So, you see, this is your experience relay. It gathers a training this sample by interacting with the environment and saves it the training data. Okay. Then you are using the training data. So suppose you have already a small Q network with random variables. Okay, some random network you have designed, and a target neural network you have designed. So you pass those training batches to this Q network and target network, and you compute the loss. Okay. Then you train the Q network only, not the target network. The target network remains fixed. Then at each every t steps, you copy the network weights to the target network. Nothing more. You just compute the loss. You train the network. You train only one network, and you transfer the weights to the T network. Nothing more. It is done. This is what it is done. So you so basically this Q network uses your so this Q network basically uses your uh, one minute. Just give me a second. I will add the diagram. So this is what your Q network does. Q neural network does. Okay. So it takes in you have your training data set, right? So you have gathered that in here. You gathered that in here, and you are using the training data. You are using that state, and you are using the Q neural network, and you are predicting the Q value. Okay. You are just predicting the Q value. You are taking this, and you are predicting the Q value of this. So what is basically the Q value? Back propagation. Yeah. So this part is the back propagation. This is where when you are training the neural network after computing this first, then you are doing the back propagation, forward propagation, and everything. So this is where you train it. This is where you train it, and then you transfer the weights to the target network. So why do you use the target network? So basically you are doing transfer learning. So both are predicting the same thing, right? Both are used for predicting the Q value. Just one predicts the max Q value of the next step, and this. And then you can apply your regular TD algorithms and all based on this to do it. Okay. Nothing how it was taught in the class. It was quite difficult to understand. So this is a much easier way to understand how DQN works, right? So to more understand it in a better way, I will suggest you go through this article. So go through this article. You can save it. This is how you do the DQN part. Okay. Any more doubt you can ask. Okay. So let's go to the next one. So the other topic you were introduced to this week. So other topic which you were introduced to this week was your food allied problem. So that uh, policy gradient problem. Okay. So let's start. What do you mean by the policy gradient problem and why it is required? So previously, what you were doing. So previously, to define a policy, you used value function and state action function, right? So to define a policy, you're trying to use these two. So uh, like yeah, both in tabular approach and your function approximation approach, you're trying to use to define a policy. You're using this value function and your state action function. So why not try something different? That is, instead of using a value function or a state action function, what if you just use the policy and action as a pair to compute the based policy? Yeah, both on and off, both, right? So if you have gone through the book, it has both off policy and on policy, continuous policy. Those both are being described there. So what we are trying to do here is in policy gradient problem, we try to learn a parameterized policy that select actions without a value function. This is what we are trying to do in the policy gradient problem. So see, this policy now we are defining as something like this: pi of a by s colon theta. So theta is the parameter we want to study. Theta is the parameter we want to learn, right? So we want to in this case we want to basically, instead of selecting the policy through your value function and all, we want to use this policy directly. So you have pi a given s, and you want to learn this value theta, through which you can predict the policy. So let's do that. So let's go get into a little deeper there. So since theta is learnable parameter, so we have to update the theta at each state, right? So theta t plus 1 we can write as theta t plus alpha j of theta, right? So basically this is your gradient. Now notice one thing, you are doing an addition here instead of a subtraction. Why? Because our task is to maximize reward, right? So our task is to maximize reward. That's why we are doing a gradient ascent here instead of a descent. Because we are trying to maximize the reward. So this is your update policy, update rule for your policy gradient method. So any doubt regarding this? Okay, so the next thing is your so what is the objective? What's the objective? The objective is to maximize reward, right? That is the objective. So we can write reward for policy pi as given all s mu of s summation a pi of a given s comma theta summation p s comma r given s dash comma r given s comma a into r. So this is the expression that is given for your reward computation for a given policy pi. That is the total reward for a given policy pi. So our task is to maximize it. Now what does what does this mean? What does this mean? So this you can say is your q function, q value or action state action pair. Let me use a different color and note it down. Q is comma I, you can think about it. So what does this give? What does this give? This is S dash comma R. Okay. So what does this give? So this is basically given what is the total reward I will get. What is the total reward for a given state and action. So that is what this computes. Next, what does this compute? This computes total. This computes total value for a state, right? So there is summation over all the actions for a state. It computes total value of a state. And what does this does? So this mu of s is determined by number of times a state S is visited in a trajectory, right? This is what this integrates. Yeah, the probability, I mean you can say it's probability, but basically it is indicated by the number of times the state is visited. Okay. So this is how you total calculate the reward, and this is something not new. You have seen this in chapter MDB chapter, how it is calculated. But I will just wrote it down again to understand. Now this is your total reward. Okay, so this is basically your j theta performance of a given uh, policy with parameter theta. This is your j theta. Now when you're trying to compute delta of this, like gradient descent of this, what will be the answer? So when you're trying to compute gradient descent of j theta,
Sir, please can you go back to the previous slide, sir?
yeah,
Yeah, so the j theta is equal to reward of r of pi.
yeah, yeah, that is basically the parameter, like based on the parameter theta.
Okay, so j theta equal to r of pi is equal to that whole expression.
That whole
Correct.
expression.
Okay, okay, got it.
Yeah.
Yeah, yeah.
So now we are trying to apply the this gradient descent operator on it. What will happen if you try to apply gradient descent on it? So if you apply the so here the gradient descent algorithm theorem comes in. So I will not directly state the theorem, but I will ultimately directly state the theorem. I will not go into the proof, but let me give an overview of how what is the problem if you apply directly delta value on it. So you see there are, this is basically a product, right? This is basically a product. So when you are applying uh, this operator, this gradient descent operator on it, so what it will be? It will be basically a chain rule. So basically the gradient descent is gradient descent is basically your differentiation, right? So you will apply chain rule of chain rule here. So the gradient descent will be summation gradient on mu of s, this whole, 1 minute, let me write it down. Okay, so this is 1 plus okay, so this is how you will represent it. So this is basically chain rule of differentiation, chain rule of multiplication, chain rule. Now one question will arise, like why will this have a gradient? Why will this have a gradient? The reason is the policy on which the trajectory is sampled changes with each upgrade. So this is actually also depends on theta. This pi s depends on theta because it changes over time. It changes as you are changing the policy. This mu s also changes. because once the policy changes, your uh, whether you visit that state how many times depends on it, right? Since your policy is changing, so this value will also change, so you have to check this gradient also. However, it is not required to compute this portion. Like, I will not say it is not required, but according to gradient policy gradient theorem, this one you can ignore, and you just only concentrate on this one. So j theta you can write as summation s mu of s summation a delta pi a given s theta into, so this you can write as q function as q of pi s comma a. This is how you this is what your policy gradient theorem states. Okay, so basically, if you are to calculate the true gradient, you have to include this part also, but you can ignore it for the time being if you are using a policy gradient, uh, due to policy gradient theorem, that you can use this one. So there is a proof of this theorem there in the book. We can you can revisit it upon the end of the class. You can go and check it out. Okay, so any doubt regarding this how this operator is coming?
So this first term will always be 0 on every upgrade and on every trajectory, right, sir?
Which one?
This the first term is, as you mentioned,
Mu
the
s,
first
mu
we can
s.
ignore for every upgrade on every trajectory. Like this term always be 0, correct? For all cases.
I didn't get your question again.
Yeah. So for this one, when we are calculating the gradient, so the first term you said is we can ignore, right? So
Yeah.
which means it's equal to 0. So
No,
this is
I'm not
particular.
saying zero. So if you have followed last class, you have seen that
Yeah,
for
yeah, yeah.
for TD error, we are getting, you are using a semi gradient, because
Okay.
for TD error the gradient was not zero, but it was not. It will not convert. It will converge, but it will not. We were ignoring that grade, like
Yeah.
that GT was the reward at T, because since
Right.
HET 0 one step ahead, it depends on basically the parameter theta, but we are ignoring that. So that's how this one also we are ignoring it, nothing more. It will not be zero, but it will have some value, but for the for this calculation purpose we are ignoring it, and we are saying that for j theta only we will use this one and we will try to converge. Okay. And basically they have done some experimentation on this, like when they have proposed it, and then seen that this part of the parameter is enough for it to converge. So just to reduce the calculation.
Okay. Got it. Got it.
So the proof is there on the proof that this delta mu s is not required. Why it is not required? There is a proof in there. Okay. So now we have this. So now we have this expression. Okay. Now we have to do. We will further simplify this. So you can write delta j theta as mu of s summation a q pi s of a delta pi as colon theta. This comes from the previous one. Okay, so we can write this as estimate of so if you remember, estimate of x is summation of x px. I hope you remember this, right? This was your estimate calculation formula. So we will try to simplify it like this. So we can ignore this part since this is a multiplication. We can write this one as this. E pi, estimate of pi, summation of a q pi s comma a pi a slash s colon theta. Right, you can write this. Now we will further simplify it. We can further simplify it as like this: e of pi as q pi s t comma at, that is basically sum over all, so this portion into delta pi a slash s colon theta. Right, now we can write it as this. Now we will use a trick. So we will multiply both top and bottom with this. Into this delta pi s comma a comma s colon theta. Okay, so now we will put this and this here, and we will write this estimation as this. So this you can write as GT into sorry I made a mistake. 1 minute, let me just rewrite it. So in this case you will write as e pi summation a q pi s of a into pi of a by s theta by divided by pi of a divided by s theta into delta pi of a s colon theta. Right, So this will come here. So we can write it this as something like this. So this, since this is a summation over all state action pair, you can write it as this. So this into this basically becomes your Q of AT STAT let me just use a different thing. So this part becomes Q of Q of phi STAT into this portion. Delta pi A by S theta divided by pi A of S given theta. Right, and this is how this comes down to. This is what it comes down to. And this is ultimately written down as, when you are calculating the estimate of this, it basically is GT into, and there is another way of writing this, is delta ln pi of A by S theta. So this is how your update function ultimately becomes. This is what your update function ultimately becomes. J of theta is equals to GT into this. So in this step, if you have any doubt, you can ask. So only step what I am extraordinarily doing here is this. From this jump to this jump, this is basically one, right? Same term divided by top and bottom. This is basically one. So we can write that. So this is only the jump we are making, nothing else. Like all else are quite same.
One question, sir.
Yeah.
In the first line, actually, why we ignore the function value? Because gradient of j of theta is equal to summation of mu of s, then summation phi of, you are writing some, then gradient is action theta, and then in the previous slide we actually, according to that, we
Mm-hmm.
take the gradient function and then we ignore the first term, and then the second term,
Yes.
there is value function, but in the first line we ignore the value function, the
So this
function
was the
of,
previous one, right? So you say which one you are trying to say?
yeah. In this, the top, the first,
This one we
yeah,
ignore.
this is we ignoring, and
Yeah.
then we are taking the second one.
Second one.
But in the second one, the last term before the value function, there is actually a function of state.
So this one you are
So,
taking.
yeah. So we are, in the next slide we are ignoring this.
No, no, I am ignoring here only. Not, I am not ignoring. So this basic, what does this mean? So I mentioned it here. What does this mean? This summation over this. What does this mean into Q? This is basically your Q function, right? What
Q
is the
function.
what is the
Yeah.
total value of a given state and action? This is what it
Action.
calculates. Right? This is your state transition, state reward transition probability, and this is your reward.
Yeah.
Right? So
Yeah.
that is what you are doing and calculating it. Nothing different is there. So you
So
can.
this whole thing is considered as
This is the whole reward. So if you remember the MDP problem when you are trying to do,
yeah, yeah, yeah,
so
yeah, yeah.
this was the whole calculation there, right? So
Correct.
I have done nothing different. We have taken the same thing here.
Mm-hmm.
What I am saying is that this is basically a Q of SA function.
Q of SA function. Okay, so can you go back to the last slide, like the one,
Yeah,
the next one, next one, next one.
yeah,
So here is we are taking it as a whole.
yeah. I'm doing nothing different. I am putting this one here and this one there. Nothing more. This function I have just interchanged it. Nothing more. It is multiplication, right? You can interchange it.
Yeah, yeah, yeah. Okay, okay, got it. Because I was a little bit confused with the previous page. The
Yeah, yeah.
okay, 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 got it. Yeah, yeah.
Okay. So this is your ultimate. This is your ultimate equation for update rule. Okay. So your update rule will ultimately become update rule will ultimately become theta t plus 1 is equal to theta t plus alpha gt delta ln pi at given st slash theta. Right, this is your ultimate update function for this policy gradient, right? So if you are using Monte Carlo, what you will do? So if suppose you are told to implement Monte Carlo policy gradient. So what you will do? So what you will do is this is on a continuous, so loop forever. So you generate an episode is 0 R0 S0 sorry S0 A0 R0 ST minus 1 AT minus 1 RT, right, using pi comma theta. So you are using you are just generating an episode using the policy pi which you are trying to find. What you will do is loop over the episode. So this episode you have generated, you will loop over it. Now what you will do? You will calculate the g. How you will calculate the g? You know how to calculate the g, right? G is calculated like this, right? G is equal to summation k is equal to t plus 1 to t gamma k minus 1 minus t minus 1 rk, right? So this is how you calculate the return. Basically you sum it up, right? You are summing the discounted sum of all the returns, your rewards, you are summing it up and you are calculating the return, and then you update the theta. Theta is equals to theta t plus alpha gamma k g delta ln pi at comma st given 0 given theta, sorry. So this is how you update the theta, right? So this is your policy gradient. Monte Carlo algorithm. Right. So any doubt regarding this? So I guess this is now quite clear. Like how are you like given any problem? So instead of Monte Carlo, if it is given TD, how will you update it? You will try to do use the same kind of thing. Okay, I will come to the TD, but this is I guess is quite straightforward. Like how you are converting a policy gradient algorithm to a Monte Carlo policy gradient algorithm, like normal Monte Carlo problem to a Monte Carlo policy gradient algorithm, right? So now let me just open another file. Okay. So now you remember. So another way you can write this update rule. So another way to write this update rule is like this. This is called reinforced with baseline. Okay. So let me just write it down. Theta t plus 1 is equals to theta t plus alpha gt gt minus b pi delta pi at slash st given theta d. Sorry, not no need to write this big. So let me just write it like this. ln delta ln pi at slash st given theta t. Right. So this is called baseline. So here instead of updating that entire g at each step, what you are trying to add is what is the difference, what is the error, like not error, what is the difference in the backup from the one you have previously estimated to the one which you have currently got. So this baseline could be anything. So one typical baseline can be average of all the returns up to t minus 1 steps. See, that could be one baseline. Baseline can be an average of all the returns up to t minus 1 steps. Okay. Now, B can be another something which you have quite recently known also. So if I write it down, I think you can recap it and understand. You can tell what it is. So B can be, we can write it as V of STW. That is basically an estimate of value function and like normal standard estimate of value function. So PST is basically your value function. So you can write your theta t plus 1 as theta t plus alpha gt minus v of st comma w delta ln pi at slash st slash theta t colon theta t. Right, so you can write it like this. Now if you are using, instead of gt you are using one step look ahead, so what you can write it down, you can write it as theta t plus alpha r t plus 1 minus plus gamma plus gamma v of s t plus 1 comma w minus v of st comma w and this term. So what is this? This is basically your TD error, right? TD0 error, right? So in this section what you are doing is we are using using both value function and policy gradient. So this is what is known as actor critic methods. So you are using both value function and policy gradient. Previously the previous written was only policy gradient, but in this case you are using both policy gradient and for like policy gradient and value function. So your so if we rewrite this one again, so if I rewrite this one again, theta t plus 1 is equals to theta t plus alpha r t plus 1 plus gamma v is t plus 1 w minus v is t plus w into delta ln pi a comma s, right? So this part so your this part, these are your critic, this is your actor, right? So this is why it is called actor critic method. So using the critic you are trying to predict the value function, and using actor you are trying to learn the parameter. Right, so any doubt regarding this actor critic function? I hope I am not saying the So is actor critic now understood? Okay. So there were other two topics I remember after critic. There was another few stuff like actor critic and function approximation and all, like policy gradient and function approximation and all. So those, I think it is not much important, not much there also in the book. So if you have followed the lecture, you can revisit it. I will not discuss it again. So I will directly go to solving some problems after this. So okay, let's come back to these slides. So this is your. So let's start solving this week's question. Uh, Give me a second. So which among the following is are advantages of using deep QN method over other learning methods that you have seen? Option A is faster implementation of the Q learning policy algorithm, guarantees convergence to optimal policy, obviates the need to handcraft features used in obviates the need to handcraft features used in function approximation, allows the use of policy algorithms rather than on policy algorithms. Option D. But other algorithms also have on policy learning schemes, right? Your normal TD and alpha traces, TD lambda, and all those also have on policy learning schemes, right? That is not an advantage. Think about it, like function approximation and all. What is one advantage that comes here? What advantage is use? No, you can use on policy also. You can use on policy also. So that is not an advantage because you have the off policy is also you can do it with TD and all function approximation also. That is not a only advantage. It is not an advantage over other algorithms, right? So what is the advantage? Convergence every most algorithm convergence. No, no. You all have missed only one. That option C is correct. So I will tell you why. Okay. So it obviates the use of handcraft features used in function approximation. I will tell you why. So this DQN was first used for Atari games, or even after that Go and all were used. So one particular feature of this that you don't have to handcraft the feature. So if you have if you remember your function approximation, you had to do a feature. What happened to this? Yeah. So what specialty you are using in DQL? We are using a neural network, right? So these Atari games and all were first tested one using your CNNs. So they were taking as input images, right? Now, if you have used deep neural network, if you have used deep neural network using CNN, so why do you use a CNN for image classification and all? Why do you use a CNN for image classification? But like you could have used normal neural networks, not CNN, artificial neural networks for using images. Why don't you use images? Why you have to come out with CNN for images? The reason is the CNN provides us thing as automatic feature identification. So you don't have to identify the features. Like if you have given a flower image, it can do the feature extraction directly, like the petal length, right, and all. So diameter, those things it can automatically detect it. So that's the reason CNNs are used here. And here also the same concept arrives, because if you are using something like CNN, you don't have to do the feature extraction yourself. It can do it on its own. So for these Atari games and all, it uses images. So it was quite easy to use CNN in this case, like quite natural to use CNN in this case. So the correct answer is obviates the need to handcraft features used in function approximation. Like if you remember function approximation, you had to use there this phi part. Like there was that phi of n. So the number of features are there, n number of features or key number of features. So that you have to do it yourself. Now you don't have to do it yourself if you are using something like this. Okay, so the correct answer is option C. Let's go to the next one. In deep Q learning, is alpha greedy required to ensure exploration, or is taken care of by randomization provided by the experienced player? What will be the answer? So in deep Q learning method, is alpha greedy or other equivalent techniques required to ensure exploration, or is this taken care of by the randomization provided by the experienced player? What will be the answer? Yeah, why it will be B? So so if you are using, so if you are using something like this, uh, a greedy, only greedy, for experience replay. So what will happen? So you have a policy pi and you generate your SI AI RI plus 1 SI plus 1, this triple this quadruples you generate, right? Now if you are using a greedy pie, so it will always select the one which is best out of it. Now you use your neural network to the prediction and all, and you update the weights according to it. So if you are always updating it using the policy, the generated policy, so what will happen? So you will not explore it, right? So whatever the policy you have, you are always using that policy only instead of exploring some random samples. So it will be a very tight fitting, right? It will overfit. It will always just get you try to fit the policy on hand and not try to get other datas into the mix. So it will always select the data set based on the policy and greedily, like whatever is the policy, I will take it. In the matches the policy, I take it. Now, if you use an epsilon greedy, so at least epsilon amount of times you will get data which is not subjected according to the policy, which is random, right? So that help you the exploration part to explore that whether there exists some other action which are better than the one which I'm trying to select now, right? So the correct answer will be P. So any doubt regarding this? Okay, so let's go to the next one. So value function based methods are oriented towards finding deterministic policy, whereas policy search methods are geared towards finding stochastic policies. True or false? So you have been given value function methods are oriented toward finding the deterministic policy, whereas policy search methods are geared towards finding stochastic policies. True or false? Why it will be true? So with value-based methods, policies are basically derived. So when you have a value function based methods, what you have is what you want to do, what we are trying to do, we are trying to find a policy from the function such that action gives maximum value, right? So that is what your value based method trying to do, find a policy for a function such that the action gives the maximum value. Now for a policy search method, what we are trying to do, So we don't have such value function thing, right? So we are trying to use gradient descent. Sorry, gradient ascent. We are trying to find an agent's policy which can be optimal. We are trying to find an optimal policy. So the correct answer is true. Notice the difference in both of them. So here the main task is your parameters, the learned parameters. So we are learning the parameters. Whereas in value action functions, we are trying to approximate a function, right? So here we are trying to learn a function. So that is a stochastic policy. We have to try a gradient descent approach to it. Whereas in value function based method, what we are trying to find an approximate function. Again, one other way to think about it. So what are we trying to find in your uh, in your value function based method? We are trying to find an approximate function regarding it, right? Such that you give an input, it gives you the value back, actual value back. What is what we are trying to find here? We are trying to find a parameter which gives you the best value. So notice the difference. So this part is clear, this question. Okay, so let's go to the next one. Suppose we are using a policy gradient method to solve a reinforcement learning problem. Okay, we are using a policy gradient method to try to solve a reinforcement learning problem. Okay, policy gradient method to solve a reinforcement learning problem. Okay, assuming the policy written by the method is not optimal, assuming that the policy method is the optimal, which among the following are possible reasons for an outcome? The search procedure converts to a local optimal policy. The search procedure are terminated before it could reach the optimal policy. The search trajectories arising in the problem are very long. The optimal policy can be represented by parameterization used to cannot be represented by the parameterization used to represent the policy. Okay, why option A? Okay, option A, one of it. Only option A. Yes, option D is also correct. Option A is also correct. So so basically it have converged to a local optima. That could be one of the reason that the policy return is not optimal. That could be one of the reason. The search procedure, other option T is also correct. The policy optimal cannot be represented by the parameterization used to represent the policy. You might have to use more parameters or less parameters. That it depends on it. There is another problem. uh, One of the reason could be the procedure was terminated before it could reach the optimal policy. Such procedure was terminated before it could reach the optimal policy, right? So it was never. So option A and option B are quite close, but that is also. So so what will be the problem if we have a large trajectory? So what will be the problem with this? So if we have a large trajectory, so uh, will it converge? So if you have a large trajectory, can it converge? Uh, the thing is, it can converge. Yeah, it can converge. So yeah, it may miss the optimality is true, but it may not also miss the optimality. So option we don't know whether it will be a local optima or not, but it will always it will converge to a any optima. Okay. Now the problem arises is that is not the that is not that it will not always give an optimal solution or not, but the problem will be that it will take a lot time. It is not that it will not converge, it will converge to an optimal solution, but it will take a lot of time. Right, but it doesn't affect the optimality. So it may converge to a local optima, it may converge to a non-local optima or something, but that is not the reason. Like length is not a problem. Okay. Okay, so let's go to the next one. In using policy gradient methods, if we make use of average reward information rather than the discounted reward formulation, average reward formulation rather than discounted reward formulation, is it necessary to consider for problems that do not have a unique start, designated as start state? So let me reread it. Is in using policy gradient methods, if we take the average reward formulation, okay, we are using an average reward formulation rather than the discounted reward formulation, okay, then is it necessary to consider for problems that do not have unique start or designated say starts state is 0, okay, what it will be? So for discounted reward, we need a start state. So we need a start state, okay, for discounted reward. But because your discounted reward like formulation is, because you have to give your like this plus alpha square rt minus 1 rt minus 2 and rt plus rt plus 1 rt plus 2 rt, and also you have to have a star state, right, in that case. But when you are doing a average reward, you don't need a designated start state. You don't need a designated start state. You take any state as you don't have need to take a unique start state. What you can do is you can just take any state, you calculate the reward, and what you have to do, you just have to average it each state. So you don't have to take a designated start state to compute it, because you don't need the, you are not taking the discounting factor, you are just simply summing it up at each step, okay. So you don't so if I write down the formula, let me write down the formula in such a case. It's called 1 by n limit n tends to infinity estimation of r1 plus r2 plus dot 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 r of n given pi right. So this is how you calculate in that case. You don't need a typically a start state in this case. Correct answer is no. Okay, so let's go to the next one. For using similar parameterizations to represent policies, would you expect in general MC policy gradient, Monte Carlo policy gradient methods to converge faster or slower than actor critic methods, assuming that approximation to Q pi used in actor cases satisfy the compatibility criteria? So it's saying that whether MC policy gradient method converges faster than actor critic methods. So that is the question it is trying to ask. So whether an MC gradient method converges faster than an actor critic method. So I give you an idea of what is an MC gradient method policy. So if you remember this, one minute. This was your MC gradient method, right? What we are trying to do in this one, and this one was your actor critic method. This one is your actor critic method. The question is which will converge first. Question is which was converge first. So, so the problem with your MC policy is Monte Carlo policy. Is that we sample a trajectory, right? Now the length of the trajectory can be anything, right? The length of the trajectory can be anything. It can be a smaller trajectory, it can be a larger trajectory, right? So your MC policy obviously like now depends, convergence depends directly on whether what is the length of its trajectory. So that it completely depends on, right? Whereas so if we now consider your actor critic, it doesn't need the whole trajectory, right? Does it need the whole trajectory? No. It only computes the TD 0 error, right? So it doesn't have to, because in that case you have the value function already. So the next state not, it has its own reward already known, and it only has the next state which is already present. It can get from the value function. So actor critic, you don't have to wait so long to converge. It will converge faster, much faster. So it will be option A. MC policy is slower than your actor critic method. So is there did you get this point? What I am trying to say, that MC depends on your basically the length of the trajectory, whereas your actor critic basically is your one hop error. One hop in the sense you don't have to, you just take the value function, get what the corresponding value is for the next state, and then you calculate the TD error and do it. Okay. Okay, let's go to the next one. So if FW approximate Q pi and is compatible with parameterization used for the policy, this indicates that we can use FW in place of Q pi in expression for calculating gradient of the policy performance matrix with respect to the policy parameter. So you have approximation, parameterized approximation of functional approximation of Q pi, and said it is compatible with the parameterization used for the policy. Then this indicates that we can use FW in place of Q pi in the expression for calculating gradient of the policy performance metric with respect to a policy parameter. So why can we do it? So you can yeah, so if you remember the theory, so you can replace Q pi of A, say, with FW S of A if the difference is 0. One of the answer is this: if the difference is 0 in the direction of gradient of pi of A. So that means if you replace this policy with this, the convergence will not be affected. So it is quite similar. Q pi of A is quite similar to FW of SA. So that's why the difference is 0 in the direction of the gradient. Another is uh, the error between q pi and f w pi. So the error between these two, so q pi is of a minus f w is of a is orthogonal to the gradient of the policy pi. So it is a better way to say that the error will be 0 between these two. Okay, so this is basically a reasoning of why, if you have followed the lectures of this week, you can get this done. Okay, so let's go to the next one. Suppose you are using an arithmetic algorithm described in the lecture where q pi is the approximated and the approximation used is compatible with the parameterization used for the actor. Okay, assuming the use of differentiable function approximates, we can conclude that use of such scheme will result to convergence to a global optimal policy, convergence to a local optimal policy. Cannot comment on the convergence of such an algorithm. So the idea behind the idea behind policy gradient and policy gradient with function approx is that such an approach will result in policy converging always. So it will always converge, but convergence can only be in local minima, but it will converge only to a local minima. Okay, so that was all the basis between your policy gradient and policy gradient function approximation. So the correct answer is option B. Okay. So I will say that this function approximation and all, the theory is too much. I mean, you don't have to remember all the description of how you are getting to the how the mathematical approach to all. I guess if you understand the theory, that will be enough for you. That will be enough to for that portion. Okay. So this was the last
So,
question.
so one question:
Mhm.
how do we tweak this policy so that it converges and it converges fast and also to a global minimum?
Yeah, so that was not part of this portion. So if you go through it, that its task is only to find, to make sure that it always converges, because convergence is a very critical problem, right? So like,
But but
if you are using a neural network, if you have done a deep learning course and all, that it is not possible that every time it converges, right?
and there is possibility that there could be more than one minima, right?
Yeah, that is always a possibility. So that is the reason we are saying it's a local optima, not a global optima. Okay, so that was the last question. Uh, so if you have any other doubt, you can ask. So thank you for joining. We'll again meet next week. Yeah. Okay. Thank you for joining. Yeah. Bye.